Alright, silly people, here's the situation. We have a wave function defined over various intervals, um, some normalization constant capital A, x over A for x is equal to 0 to A, and then um, capital A B minus x over B minus A for A to B. Um, and we need to normalize it, so we need to find what the normalization constant capital A is. Um, that is done using this normalization condition for wave functions in position space. The integral over all space of the square modulus of the wave function um, is 1. What that means when we translate it into our situation is we're going to just integrate from 0 to 1 of the wave function square modulus from 0 to A, and then another region from A to B because it is discontinuous. Right. So taking the square modulus of the stuff in the first region, you'll end up with an A squared over A squared, capital A over little a, both squared on the first term, doing the integral of 0 to A of x squared dx. And then the other term, a squared over b minus a squared times the integral of 0 from a to b of b minus x squared dx. First integral's not too bad. It just ends up being x third over 3. And then the second integral, I'm going to just expand the polynomial inside the integral before I do anything to it. B squared minus 2xb plus plus x squared. And then evaluate the first integral. It's going to be a third over 3. And the second integral, actually doing the integral, you'll get b squared x minus xb plus x cubed over 3 x squared b. That is from A to B. Simplifying the left side, a squared will cancel out a squared. You're just going to have capital A squared times a over 3. Second term, evaluate the integral at the bounds, so it's going to be b third minus x, or b third, okay, plus b third over 3 minus b squared a plus a squared b minus a cubed over 3. Okay. Let's factor out a 3 from the second term. So we can have it a squared over 3 out here. And then a plus 1 over b minus a squared. Where the b cubed terms will cancel out. Well, those ones will. This one sticks around, so b cubed minus 3b squared a minus, or plus 3a squared b minus a cubed Sure. Okay. At this point, it's good to recognize that the stuff inside the brackets is actually just b minus a cubed. So I'm just going to prove that real quick. That's b squared minus 2ab plus a squared times b minus a, which is b cubed minus b squared a. Minus 2ab squared minus 2 or plus 2a squared b plus a squared b minus a cubed. Combining like terms, b cubed is b cubed minus 3ab squared plus 2a squared, 3a squared b minus a cubed. Yeah, so yeah, the term inside the brackets is just b minus a cubed. Applying that to the result of our integral, capital A squared over 3a plus b minus a cubed over b minus a squared. One of the factors of b minus a squared will cancel out, so it's going to be a squared over 3a plus b minus a. So you got a squared b over 3. Now that has to be equal to 1. So you just solve for a. You get 3 over b under a square root. Right. That's the normalization constant. Now check this out. If you wanted to sketch the wave function, then you would do it much like this in this Desmos window. Just check this out. Whenever you change the value of a, you're just changing the x position of the vertex, moving back and forth like that. If you change b, then you're changing the height of the peak. The height of the peak being equal to the square root of 3 over b, and b being the x position of the terminal point on the other side of the wave function. So that's how you would sketch it. What does that mean for like the most likely point that the particle will be in? It means that it's going to be A. So A is the part of the box that is most likely to have the particle at t equals 0. If you wanted to find the probability of finding the particle to the left of A, well, then it's much the same process. It's just now we have a normalization factor, so we can actually do it. So now we're just integrating from 0 to a, the wave function, or the square modulus of the wave function, right? So it's a squared over a squared integral from 0 to a x squared dx. A we found was root 3 over b, so a squared is just 3 over b, so we're doing 3 over b a squared. Oops. And then the integral is x cubed over 3 from 0 to a, so it's 3a cubed over 3ba squared. So the probability that you find the particle to the left of a is exactly equal to a over b. All right. Now we have to look at the expectation value of this guy, which you're going to be integrating over all space x times the square modulus of the wave function. This is a more complicated integral. So again, splitting it up from 0 to a and a to b, you got capital A squared over a squared. Yeah, capital A squared over a squared. 0 to a, just x third dx, and then capital A squared over b minus a squared, integral from 0 to, or from a to b, x b minus x squared dx. All right. Using our definition of a, we have 3 over ba squared right there, and then that integral is actually still pretty easy, x fourth over 4 from 0 to a. This one, going to expand the polynomial, so b squared minus 2bx plus x squared going to apply the bounds to the first integral, so it's going to be a fourth over 4 on the second one. I'm going to distribute the x through, b squared x minus 2bx squared plus x cubed dx. Simplifying the left term, it's 3a squared over 4b. And then, I don't know why I haven't used the definition of a yet on the second term, so 3 over b times b minus a squared. And then now the integral can be evaluated, so it's b squared b squared x squared over 2 minus 2b x cubed over 3 plus x fourth over 4 from a to b. I will go ahead and apply the boundaries. 3 over b times b minus a squared, all of that, times b fourth over 2 minus 2b fourth over 3 plus b fourth over 4 minus b squared a squared over 2 plus 2ba cubed over 3 minus a fourth over 4. Okay. If you want to simplify that, I'll leave that as an exercise for you. I'm not going to do it because it's just algebra, and I really don't want to do it. All right.